Hi! In this video you will be entertained by an expert in industrial biotechnology. Professor Wim Soetaert is a teacher at Ghent University and also the founder and head of the research lab InBio. He is a quite busy bee, as he also is the co-founder of the spin-off company InBios and founder and CEO of the Biobase Europe pilot plant, which are all situated in Ghent, Belgium. So he will explain you about the integrated bioprocess design, which consists of a combination of biocatalyst engineering, which can be enzymes and microorganisms, the development of the production processes with these biocatalysts, followed by the scale-up of the developed processes. The combination of all this will enable application research and market seeding, and eventually all of this will enable the commercialization of new bioproducts such as new biosurfactants. Enjoy!
In this video we will explain how the integrated bioprocess development actually works. So first of all we start with the strain and enzyme engineering. Secondly, we need to develop the fermentation of biocatalysis process and the downstream processing and also scaling it up to a larger scale. And third, we need to have application research. For the strain and enzyme engineering, we basically have two options. Either there is already a natural process that produces the compound that we are interested in. In that case, we need to improve the process. The second option is when there is no such process, so then we have to start from scratch. And usually this means that we have to introduce new genes into a conventional, normal, harmless microorganism to actually produce a new microorganism that produces the substance. The genetic and metabolic engineering of microorganisms, we need a number of techniques of synthetic biology. First, we need PCR, polymerase chain reaction. Secondly, we need the transformation to introduce the genes and the DNA into the microorganisms. And third, we need colony PCR to detect actually the desired microorganisms so that we actually end up with a good engineered microorganism. Once we have developed a suitable strain, the next step is to develop the process. So this consists of medium development and also the optimization of the fermentation parameters. So when it comes to medium development, we can do that here in an Erlenmeyer flask. But to move faster, we can also do it in these 96 well plates. So we can test 96 different medium compositions at the same time. So the analysis of the bioproduct is very important. For instance, if we are developing the medium in this 96 well plate, we need to analyze in all 96 well plates how much product there is actually produced so that we can actually determine which is the best medium. After the strain development and the medium optimization, we need to do the process development. We start on a lab scale like here, so we start by doing fermentations on a 1 to 5 liter scale to develop the various fermentation processes such as dissolved oxygen, pH, stirrer speed, etc. And as you can see, we do several different fermentations, very often at the same time with different parameters, so that we can very nicely see what is the effect of these parameters on the production of our final bioproduct. After the bioprocess, which is a fermentation or a biocatalytic step, we need to purify the product in a pure form from this very complex mixture of cells, enzymes, metabolites, etc. in order to get to a pure form. And this is a process which we call downstream processing because it is downstream from the bioprocess. Now, depending on which is the bioproduct, your downstream processing operation can be very different. And first, of course, we start to develop this on a lab scale with equipment relatively small scale, as you can see here, until we get, say, the first 10 grams of our product, and then we need to analytically check whether the purity is good enough and the quality of the product is good enough to be fine. And everything comes together when we have the best strain and the best process, and then we can proceed to the next step. And then the next step is actually the scale-up, which happens in a pilot plant. So to scale up a process in a pilot plant, one needs pilot plant equipment, and unfortunately a pilot plant is very expensive. Big companies sometimes have their own pilot plant, so they can do their own development, but smaller companies don't have a pilot plant. However, also for smaller companies there is a solution. They can use an open innovation independent pilot plant, such as the Biobase Europe pilot plant. So in the pilot plant, first of all, obviously we demonstrate that the process also works on a larger scale. Secondly, we generate data about the process, but also data of the economic impact, because obviously a bioprocess has to be economically feasible, and also data on the environmental impact, which is within the framework of a so-called LCA, or life cycle analysis of the bioproduct. So one of the purposes of the work in a pilot plant is first of all to demonstrate the process, but also to actually produce product in a larger quantity. So whereas in a lab scale we have produced 10 grams, in a pilot plant you can produce kilograms up to tons of product, which is also very important because very often people need sufficient quantities to do application development of your new product, and for that obviously you need sufficient product. So in order to get a new bioproduct to the market, so we need this integrated bioprocess development. Very often this process is not linear. It's not so that you can say we do 1, 2, 3, 4, 5 and we're done. Very often there are iterations. What you sometimes see is that a strain which works very well in a lab scale does not work very well on a large scale. Then you have to go back to the lab for a renewed strain development, then go back to the medium development, scale up, pilot plant. So very often this process is iterative. This is what we call integrated bioprocess development, and we need all of these processes to actually get the bioproduct up to a commercial scale.
Now, I hope you enjoyed it and are now contaminated with our enthusiasm to make bioeconomy work. Goodbye!